So I trust people can hear me. My mic seems to be working. Nobody's complained yet, so that's great. All right, so welcome back to Chemistry 2330. I'm, again, Dr. David Irvin. Go ahead and write, if you have a question, go ahead and put it in the Zoom group chat, or you can ask a question by unmuting yourself. That is perfectly fine. I wanted to go over our administration for this week. You should have all be logging into Top Hat now because homework was due last week. And according to my Top Hat report right now, I have a few students. I have 80 students registered, so that might be everybody. I do have about 10 people down here that I had sent invites to. I'll double check and make sure they're on our list here, but I think everybody else seems to be in and doing well, which is great. I have grades for, it's brewing on the background there. Do you ever notice how on Top Hat it always says brewing some tea? You know, they're Canadian, so you know it's very polite. Anyway, so that's why that happens. I talk to them a lot online, and they're kind of funny. They always want to know what it's about. So, and let's see. I've got a whole bunch of grades in for Chapter 1, so that's great. Great. An average on the homework was 8.43, so that's wonderful. People are doing quite well then. Okay. Also, this week is, of course, now that you're here, you obviously know that we have our new Zoom chat every week. I again send those out by Canvas. So that has to go through your official Texas State ID. So, and if you go through Texas State's Zoom, you don't get put into the waiting room. But I think I've let everybody in so far right now. Okay, so we'll do our goal slides, which are on Top Hat and what I have here. And then you'll see that there are full slides available, I want to say, files. There's full slides. Those are the slides that are covered on every single video. Those are also under files. It's called slides-videos. So if you want all the words in there and everything spelled correctly, those are the slides that you would look for that. But the goal slides you'll see are slightly different. Now, remember that the goal slides are things I'm going to focus on because they are the tougher portions of the chapter. That does not mean you do not look at the other videos and look at the other details in the chapter. The goal slides are these things that I'm bringing, you know, your focus to. So you can't do, you know, just one or just the other. Well, you probably could just do the videos and the slides, but the goal slides gives you an opportunity to ask questions and need to focus on the really hard stuff. Or the complicated stuff. Nothing's hard. It's just fun. Okay, so then that is, and the last thing on our due this week is that we have our homework for this week is due on Friday at midnight for Chapter 2. So we're going to completely cover Chapter 2 today, and we will not start Chapter 3 until Wednesday. Okay. All right, are there any questions before we begin? We have about 57 people online. Yes.
Yes, Professor, I have a question. So I emailed you asking you about the SI sessions and you replied to me with a link. When I opened that link, it says it's not available or there is no survey going on.
Yeah, we do not have SI sessions for this class. This is 2330. I only have SI sessions for 2341.
The 2341.
Yes. And so that's the organic 2-semester organic class. So we don't actually have SIs for this class.
Okay, because for the first day when I reviewed the recording from the Zoom meeting, it was like somebody talking about the SI session.
That must have been on the other class, the Chemistry 2341.
Oh, okay, okay.
Yeah, so 2341 does have SIs, our class does not.
Okay, gotcha. All right, thank you.
Okay, so any other questions before we begin? Okay, so I'm going to start with Chapter 2, Goal 1. Okay, so chapter 2 is all about acids and bases. And when we took Gen Chem, however many months, weeks, years ago it was, we learned that, you know, acids are things that had protons and that they dissociate water and they lower pH. Okay, and that is true. However, in organic chemistry, we look at acids and bases a little bit differently. And the reason we do that is so that we can take that traditional inorganic acid definition and expand it to be used in our organic reactions as well. Okay, so I'm going to go ahead and share my screen. And come on, share. There it goes. All right, good. You never know. Sometimes it does, sometimes it doesn't. Okay, I'm putting my gallery view up over here so I can see everybody and who has a ceiling fan. Okay. All right, so you should be seeing my chapter 2 acids and bases here. And this is again, chapter 2, goal 1. Okay. So the 3 goals we're gonna cover today are Lewis acids and Lewis bases. Okay. Now, if you remember one definition about acids and bases in the class, remember the Lewis acid, Lewis base. Okay. That is the most important one we use because we can actually, in goal 2, we'll see that that actually covers the others. They just have different definitions about how things happen. And then goal 3 is what we're going to call Pka and conjugates. Okay, so Pka will give us a scale, a relative scale of which is more acidic or less acidic. And the idea that if you have an acid and a base pair, and then when you react them, they turn into a different acid or a different base, what we call conjugates. Okay, so you never actually just completely neutralize something. It always turns into a conjugate acid-base system in organic chemistry. Okay, so let's go ahead and talk about Lewis acid and Lewis base. Okay, so Lewis acid and Lewis base is it's the same guy from Lewis dot structures. Okay, so he has this really elegant way of describing how things are happening. Okay, so in the case of organic molecules, we want to describe every molecule as either a Lewis acid or Lewis base. Some of them are so weak they never act like that, but we can describe every single molecule this way. Okay, so the key here is a Lewis acid is a molecular ion that can form a new covalent bond by accepting a pair of electrons. So the Lewis acid accepts electrons. Okay, now a Lewis base is the opposite. A Lewis base is any molecular ion that can form a new covalent bond by donating a pair of electrons, okay? And I'm sorry that when I did the conversion here in PDF, it kind of overlapped them. But I want to blow up this little example here, okay? So this is the simplest definition of Lewis acid, Lewis base. And you'll notice that the Lewis base usually has a lone pair. It can have an ion or a lone pair. That lone pair are the 2 electrons that are being donated to make the new covalent bond. Remember, your covalent bond, your sigma bond is 2 electrons. Okay, so the idea is the acid is anything that can accept those electrons to make that new bond. And the base is anything that can donate that pair. So acid accepts, base donates. Acid accepts, base donates. Okay, and let's go into that a little deeper. Okay. So this is the absolute definition we will use on everything we do in this class. Okay, so let's think about that in a more classical sense. What we thought about in organic chemistry was that HCl dissolves in water, dissociates in water. HCl is a strong acid, and the acid portion of that is the hydrogen, right? And then the water is the part that's reacting. So if we have HCl, which as a gas has a covalent bond between the hydrogen and the chlorine, it's a polar bond, but it's a covalent bond, okay? And we put that gaseous HCl in water. The lone pair on water is going to act as a base and reach out and make a new bond with that hydrogen. And so the hydrogen is accepting those electrons to make a new covalent bond. Now, what happens to the chlorine? Well, the electrons that were bonding the hydrogen and chlorine together go on to the chlorine, giving it a chloride ion or the negative charge. Okay. So what we've done here is we've taken water as a base, HCl as an acid, and we have reacted them. Okay, so now what we have is we have hydronium ion, which is our inorganic acid, and our chloride ion, which turns out to be our conjugate base. And we'll talk about more about that as well. Okay, so now that's in a classical sense, but we're in organic chemistry, so we want to start thinking about organic molecules and how they react as Lewis acids or Lewis bases. So in the case of HCl, and we want to use an organic molecule, we can use something like methanol because it has half of the water structure and the OH, and a hydrogen that will bond there, but then it has a carbon on it, so it's more organic. So we can look at it that way. So in the case, if we draw the Lewis dot structure of our methanol, we see that it has two lone pairs, okay? So one of those lone pairs can act as a Lewis base, reach out and share those electrons with a hydrogen that will then ionize and give us the proton transferred to the oxygen, our Lewis base, our hydrogen was our acid, and now we have that new covalent bond between the oxygen and the hydrogen, creating what we call the oxonium ion, because it's no longer hydronium because it's not water, but it's on oxygen, so it's oxonium ion. And then we have the chloride as the counterpart to the charge there. So again, the organic molecule with the lone pair is acting as the base. The hydrogen in this case is acting as the acid. So everything should make sense as far as acids and bases so far, because it's really similar to what we saw in inorganic chemistry. Okay, but we're explaining it from the point of view of the organic molecule. Okay, so let's look at what things can act as Lewis bases in organic chemistry. Okay, so when we think about things like water, water is acting as the base when it dissolves those. But we have a lot of organic molecules available to us. So let's start on this left side of the screen here. And I'm going to start with, let's start with blue here. We have right here the halogens, okay, the halide ions, right? So each of these halogens has 4 lone pairs around it, right? So it has electrons to donate. However, they are all electronegative atoms. They are very electronegative atoms. They're the farthest over on the scale, right? So they're in the group 7 here. They're the farthest on the periodic table. So the fact that they are so electronegative, they don't mind being ions, okay? So that makes these halogens weak bases because they don't mind being ions. They don't have to share their electrons, okay? So if we move one group over from the halogens, we have oxygen, okay? So it's a little less electronegative than the halogens are, but it still has those lone pairs that it can share. And because it's more electronegative, so it doesn't mind having those electrons, but it has electron pairs to share, it is a weak Lewis base. It will share those electrons if there's a reason to. Now, so this is our group 6. This is group 7. This is group 6. This is group 5, nitrogen. Less electronegative than the other 2 elements, right? So it doesn't want to hold on to those electrons as tightly, so it's more willing to share those electrons. So it makes it a stronger than the OHs. It makes it stronger than the oxygens. And so we call these strong bases. So the amines, the neutral nitrogen compounds, are strong Lewis bases. Okay. Now, once you go over one more and you actually have a full charge on oxygen, that makes it even stronger. It already has that negative charge, but it has a total of 3 lone pairs. Those 3 lone pairs can share more readily than the 2 lone pairs in the neutral species, and therefore it becomes a stronger one. So we've taken our group 6 and added a negative charge, and it became stronger. Now we get to the strongest of our Lewis bases. It's a nitrogen. It was strong, and now we gave it a negative charge, and now it's our strongest, our very strong Lewis bases because it's got a negative charge and it's not as electronegative, and it really wants to share those electrons. Okay, so my rationale is stepping you through the periodic table and showing you that strength correlates to electronegativity is important. And we're going to talk about that again. Okay, but by just kind of rationalizing, oh, group 6, then group 5, then, oh, and then we add charge and it does it again. So that's the goal I want you to keep in your head when we talk about Lewis bases. All right, questions on that real quick? We're up to 57 people. That's pretty good. Okay. Now, that is not the only kind of Lewis acid we are going to find in our organic chemistry here. One of the things we're going to find out in about 3 chapters is the idea that other things can act as Lewis acids, specifically things that already have a positive charge on it. If something already has a positive charge, then it wants to share electrons with something so that it can turn back into a neutral species. And so the classical one that we will be using a lot is what we call a carbo cation. So it is, by definition, a carbon, carbo, and it has a cation on it. So it's a carbon with a positive charge on it, okay? So the reason it can be a Lewis acid is it really, really wants to get those electrons, and it'll react with even very weak Lewis bases to do so, okay? So in this case here, we have our bromide ion acting as our Lewis base. Remember, that was the weakest base we had on the previous slide, and it will share those electrons with that positive charge on carbon, creating our new sigma bond, okay? So before, up to now, the only Lewis acid I showed you was hydrogen. Hydrogen was transferred from an acid to a Lewis base. Here I'm showing you a different kind of Lewis acid, something that wants electrons to fill its octet. Okay, so I talked a little bit about how electronegativity changed basicity, but I want to talk to you about the 4 factors that change the relative acidity of an organic compound, okay? And it also tells you about the relative stability of the anion formed when you deprotonate something or remove a proton with a base, okay? So the 4 things to consider about whether or not it's going to be a more or less acidic are, first is electronegativity. How much does that atom want to have the electrons? Okay, the more it wants those electrons, the easier it is to remove that hydrogen. Okay, second thing is resonance stabilization. Remember when we were drawing Lewis dot structures and we drew an acetate or a carbonate ion, and we could draw that negative charge moving around on different oxygens? So that would be resonance stabilization. If you can share that charge over more than one atom, that's going to increase the acidity because it stabilizes that charge. The next thing we have is the inductive effect. What that means is if you have adjacent atoms that are electronegative, that's going to pull electron density away from the atom it's actually bonded on. And the last thing is our size and delocalization of charge. This works best with the halogens. And if we think about it, fluorine is the most electronegative, and it's very, very tiny, right? But as you go to chlorine, it got bigger because it has extra shells. Bromine's even bigger, and iodine's even bigger, okay? So our iodine is going to have a different acidity than fluorine. Even though fluorine's more electronegative, iodine can spread that charge out. And we're going to see a trend in that when we look at that. Okay, so let's talk about electronegativity. Okay, so we've already talked about how electronegativity increases as we go toward fluorine and we go up for fluorine, because fluorine is the most electronegative atom we have. So let's just look at hydrogens attached to atoms along that group 2, that first row there. So if we look at the pKa, which is, it's the log of the equilibrium constant of acidity, okay, we'll get into that a little bit later. But the relative idea here is the lower the number for pKa, the more acidic something is. So things like HCl have negative numbers. They are so low that they are less than 0, and they are very strong acid. Okay. So as you go closer to 0, they get stronger. As you go away from 0, they get weaker in acidity. So let's look at those elements as we move down the table. So fluorine is our most electronegative atom, right? And so of this group, it has the highest acidity. It's the closest to 0 at 3.4. Okay. If we move over one group, that's taking it to oxygen. The hydrogen on water actually has a pKa of 15.7. Okay, so we would consider that, you know, like that's one of those things that can be an acid or a base, and so it's one of those things we use a lot as, oh, is it greater, more acidic than water or less acidic than water? So that's something to keep in mind. So if we move from, yes, question? No? Okay. So if we move from group 6 to group 5, we've gone down in electronegativity a little bit, and the acidity drops, okay? So our pKa has gone up to almost 40. So we've moved over, you know, about 20 points here. And so it became less acidic by being less electronegative, okay? And then when we move just one more group over, we have what we consider one of our least acidic protons, and that's the proton on a carbon atom. So this carbon-hydrogen bond is almost nonpolar, and carbon has such a low electronegativity in comparison to the other elements that that bond is really not very acidic at all. You have to pull it off with very, very, very strong bases. So just looking at electronegativity, it's more acidic as you go toward fluorine on the periodic table. Okay. So if all ions were the same size, there would be the same trend as we see the electronegativity on your periodic table. Okay, so the next factor, first is electrophilicity. Second is delocalization. Okay, so when we drew those Lewis dot structures for the carboxylate ion and the acetate ion, we saw that we could draw one Lewis structure where the negative charge was on oxygen. And then by just moving electrons from one oxygen down to the other, we could then move that negative charge to the other oxygen without changing any other of the bonds. Okay. Which means we had part of the time the negative charge is on one oxygen, so part of the time the negative charge is on the other oxygen. Okay. So if it's flipping back and forth, this oxygen has half a negative charge and this oxygen has half a negative charge. Because we're delocalizing that negative charge, it makes that proton more acidic. Okay, so let's talk about water again. Water is what we kind of consider our baseline. Is it more or less acidic than water? And if you remember, our water is about 15.7 pKa, but acetic acid is more acidic than water. It has a pKa of approximately 5. Okay. So, and that has everything to do with the idea that we could put that negative charge on either of the oxygen and the carboxylate. So let's take that and see the difference between the resonance and the electronegativity. So if we looked at just the carboxylate ion, oh, it's an oxygen, right? Let's look at an alcohol that can't delocalize its charge, okay? So we have the same electronegativity for both elements, both atoms are both oxygen. And so we should have the same electronegativity. So the only difference in the pKa or the acidity should be that delocalization. Okay. So if we look at an alcohol right here, and we measure the pKa using any base, in this case we're going to use water as the base, we find the pKa is about 15.9. Remember, water is 15.7. So that means water and alcohol have about the same acidity. Okay. And it's much higher than that of the carboxylic acid. So it's not the electronegativity changing the pKa of the carboxylic acid, it's the delocalization. Okay. So that's how that's why the carboxylic acids are always more acidic than their other oxygen counterparts. Okay, and here's why. Okay, so because we can share that charge over two different atoms by looking at our resonance, we can move that charge back and forth, back and forth. It makes it easier to lose that. If we look at the alcohol right here, that negative charge stays on that oxygen. It does not change. It does not go anywhere. There's no place for it to transfer to. It can't go and be on an oxygen because you have to lose a hydrogen to do that. So it is much less acidic than the carboxylic acids. Okay, so that was 1 and 2, which is electronegativity and delocalization. Number 3 is what we call inductive effect, okay? So in the inductive effect, we have an atom adjacent to the thing that's acidic, okay? And what we mean by adjacent to it has to be at least one bond away. It can't be on the atom that is getting the charge. So, and the classical example for this is, let's look back at acetic acid. We just learned that acetic acid is acidic because of its delocalization, okay? Now, we also learned that electronegativity can increase acidity as well, okay? So, but what if you want to look at the acidity and you have an electronegative atom nearby? Okay. So in the case of our acetic acid here, we have hydrogen and carbon, and they have about the same electronegativity. Hydrogen's about 2.2, carbon's about 2.5. And so that's a fairly nonpolar bond. There's not really a lot of anything being donated back and forth. If anything, there's a slight donation of electron density to this carbon here. Ever so slight, because that's a very nonpolar bond. However, if we took those hydrogens off and replaced them with an atom that had an electronegativity of 4, in this case, fluorine, what's going to happen is those become polar bonds now. Okay, and instead of donating slight electron density to the carbon there, it's actually going to pull electron density toward those fluorines. Okay, if those fluorines are pulling electron density away from that fluorine, that means that this carbon is less electronegative, and it's going to be pulling electron density away from the carbon right here. When it does that, it makes it less negative. The charge over here is less negative because some of it's being pulled into this carbon, and it becomes more acidic. So anytime you see a lot more electronegative atoms adjacent to the acidic site, you should see an increase in the acidity because of it. Okay, so that brings us down to our last thing, okay? So we kind of saw that the more stable the ion, or the more you could delocalize it, that we saw an increase in acidity. Okay, so that works, delocalization works with molecules or ions of molecules here. But if we want to look at just ion size, as far as we want to look at the atomistic ion size, we have to look at the halogens and look at the relative acidity scale we see in the halogens. Okay, so if we look at fluorine, chlorine, bromine, and iodine. Iodine's the bottom, and it's the largest ion, okay? And it's not as electronegative as fluorine, although it's still fairly electronegative, okay? The biggest difference between them is the idea that the iodine is about 3 times the size of that. And so we have 8 valence electrons spread out over a much bigger surface area, okay? Being able to spread that, extra electron, to get that 8th valence electron over a much larger area means that it will be more acidic because it can stabilize that charge. So in this case, especially with the halogens, HI, or hydroiodic acid, is going to be the most acidic of the acid halides. The hydrogen bromide is going to be the second most acidic. HCl, we know, is a very strong acid. And HF technically is not a strong acid because its pKa is above 0. Okay. So what we see here in this series is that HI is actually more acidic than HBr, which is more acidic than HCl. And it all has to do with that ion size. Oops, not that, there we go. Okay.
I have a quick question.
Yes.
So you're saying that when it's pulling the ions away from the more normalized charge, does that mean that it becomes more acidic?
Yes, in the inductive effect, if you have any electronegative atoms adjacent to the spot that is going to actually form that negative charge, think of it as, it's pulling the electron density from that negative, the negative charge required to make the that had the proton leave. And anytime you can make that charge spread out or less intense, it increases the acidity of the
Okay.
compound.
Okay,
So we
thank
see
you.
that same effect in the big ion, in the ions, because ion is so much larger, it also helps increase acidity.
Okay,
Okay?
thank you.
Dr. David.
Yes.
So probably just repeating what you just said, but you were saying it's one that's adjacent to like any charge or just adjacent to anything electronegative?
It can be, the most pronounced effect is when it's one or two bonds away from the thing that's going to form the negative charge.
Okay.
So, and each bond you move over, the effect gets less and less and less because it has to pull through more and more bonds.
Yes, sir.
Okay? So the closer it is to that charge that's going to be negative, the more acidic it's going to be.
I appreciate that, Dr. David.
All right. So that is the four things that affect acidity in addition that we'll see as we move through this, and we'll say, oh, that doesn't look like an acid, but wait, it is. And it's a Lewis acid. Because remember what our definition of Lewis acid is. A Lewis acid is any molecular ion that can form a new covalent bond by accepting a pair of electrons. And a Lewis base is any molecular ion that can form a new covalent bond by donating an electron pair. Okay, so this is the big, imagine this is the umbrella definition for all acids and bases in organic chemistry. Okay? So if that's the umbrella definition for all acids and bases, let's move on to goal 2, which is the other acids and bases we've already learned about, okay? So if we look at our original definition in Gen Chem or in inorganic chemistry, we saw that an acid was something that has a proton and that a base was something that that proton got transferred to, okay? So you have something that a proton is on there and can move, and it can be transferred to something else. So that was the acid and that was the base. However, let's, using this new definition of Lewis acid and base, think about that reaction. In this case, the hydrogen that gets transferred is still the Lewis acid because it's accepting a pair of electrons from the water to make that new bond. And the water is our Lewis base because it had the electrons that is being used to make the new bond to make that hydronium ion. Okay, so Arrhenius wasn't wrong, but by definition, Arrhenius must have water in the system, and a proton must be transferred. So the next type of acid base we say in our book here, we call it the Bronsted-Lowry acid and base, okay? And the reason the Bronsted-Lowry acid and base was we wanted to get away from water. You could do it with things other than water, okay? So in Bronsted-Lowry, a proton, or hydrogen plus, is transferred from the acid to the base, okay? So that's the requirement for a Bronsted-Lowry acid basis. But if you think about it, the acid is the proton donor, okay? So that means that that proton is accepting a pair of electrons from the other compound to make a new sigma bond, a new covalent bond. And the base is the one that had the electrons that reached out and grabbed that proton away from the acid or proton donor. So let's look at that definition here again. So in this case here, we have 0 water, but we are still transferring a proton. And in this case, we have, this is our lone pair. So our base is going to reach out and grab that proton, leaving the electrons that was already bonded to it behind. Okay, so in this case, this is our Lewis base, and this is our Lewis acid. Okay. Okay, so Bronsted-Lowry wasn't wrong. It just wants to only transfer a proton. So that's why the Lewis acid-base theory works for all three acid-base systems. Okay, so to put a little fine point on it, Arrhenius has to have water, and when the acid dissolves in water, it makes the hydronium ion. And when an acid dissolves in water and forms the hydronium ion, the counter ion formed is the hydroxide. So the base is always hydroxide and the acid is always hydronium ion. Okay. Now so for example, whenever we dissolved HCl into water, it always formed the hydronium ion and then a halide ion. If we added hydroxide to the mixture of hydronium ion and chloride ion, it would drive it back to water and make a salt. And that would be neutralization in Arrhenius acid-base chemistry. Okay. So the bases we typically use were the ones we saw in inorganic chemistry: potassium hydroxide, sodium hydroxide, magnesium or calcium hydroxide. Okay. So that when we have that hydroxide compound dissolve in water, it breaks up into your metal salt and your hydroxide ion. And the hydroxide ion was the base used in the system. Okay. And we even did one that wasn't a metal, where we did ammonia right here, and we reacted it with water to protonate. This is actually acting as our base. This is acting as our acid to generate a species here and the quaternary ammonium salt plus hydroxide. Okay. But again, it fits the Arrhenius definition of acid and base because it uses water and transfers a proton and or creates hydroxide ion. Okay. So let's look at it kind of from a different perspective. Let's look at from our Lewis dot structure and see where the electrons are flowing and see if it meets our definition of Lewis acid, Lewis base. So in this case here, we have something that already has 4 protons on it. And we learned from our previous goal slides that it was a base, and it's a base because it has that lone pair. So what's going to happen is these electrons are going to reach out and start to form a new covalent bond with that hydrogen. Notice that there's never just a positively charged hydrogen or a proton floating around without electrons around it. Yeah, it doesn't happen. It doesn't really do that. It always has some electrons around it. And so when it does that, it can take the electrons that it was using to bond to the other atom and leaves that on that species. Notice that the charge is left on the more electronegative atom. So oxygen is more electronegative than nitrogen. And so it'll transfer that proton, generating our hydroxide ion and our new proton donor. Okay, now we can actually take this and do the reverse reaction and donate this proton away as well. But we'll do that later. Okay, so in the Bronsted-Lowry definition, it's similar to Arrhenius, except that it doesn't have to have water, okay? But a proton must be transferred, which means an acid is always a proton donor, a base is always a proton acceptor. Okay. Now, the key thing that Bronsted-Lowry added to this system was the idea of a conjugate base and a conjugate acid. Because when a species reacts as an acid and has transferred a proton, it now can act as a base because it now can accept a proton. So we call an acid that has lost its proton a conjugate base because it can now accept a proton. Now, that means that whatever you transferred that proton to now has more protons than another thing, and it is now can transfer that proton away. And we call that the conjugate acid. Okay. So if it was an acid, it became the conjugate base. If it was a base, it became the conjugate acid. And this pairing is really important because knowing which is the more acidic, the starting acid or the conjugate acid, tells you which way the equilibrium will lie. How far will these species go on either side of the equation? Okay, so let's look at what that would look like in a balanced equation here. So again, going back to basics that we all understand is that when you take HCl and you dissolve it in water, it reacts with water to create hydronium ion. Okay. So in this case here, we know that HCl, if it was not dissolved in water, we would call that an acid because it has a proton to transfer. Okay. When we add it to water, that oxygen had 2 lone pairs on it, and it can accept that proton. So it is our base because it can accept it's a proton acceptor. However, once you take that proton away, you've now generated chloride ion. And we saw that on that acidity scale that chloride ions were weak bases. Okay, so by deprotonating your HCl, you have turned that chloride ion into a conjugate base. It was an acid, now it's a conjugate base. And just the opposite of that, our thing that had the protons that we could, had the electrons that could form that new bond, now becomes our conjugate acid. It had the electrons to use, and so it used those electrons to make that new bond. So it acted as a base, but now it's our conjugate acid because now it has the proton that can be transferred. Okay, so understanding this, an acid becomes a conjugate base, and the base becomes a conjugate acid is important to understand, and that's actually where we end up getting our pKa scale from, measuring how these things interact together. Okay, so let's go ahead and do this with organic compounds so that we can see how much closer it gets to our Lewis acid definition. And so we saw that, acetic acid is an acid because it can transfer that proton, and it's pretty acidic because it has delocalization, so that helps. And we have ammonia, and I'm going to go ahead and I'm going to draw that lone pair on ammonia because we saw that was on our Lewis base scale as well. So the lone pair on ammonia is going to be the part that acts as the base. Okay. So once that proton is transferred from our acetic acid to our material here, to our ammonia, we now have generated an ion, right? Now, once we have an ion on an electronegative atom, it becomes a base now. It has electrons to donate, okay? And our ammonia that was acting as our base now has an extra proton on it and a positive charge. So it is now our conjugate acid. Excuse me. Okay, so this conjugate acid pair thing is simple but important. Okay, so let's actually look at where the electrons are flowing here to get a better idea of the fact that it is a Lewis acid base reaction. In this case here, we have those electrons reaching out to form that new covalent bond with the hydrogen. Again, it's never just a proton floating in space. The electrons that were used to make the bond with the hydrogen are put back onto that oxygen. And again, we can delocalize this over the other oxygen, generating our ion. Now that we have a negative charge on there, it can now act as a base. It can now share electrons. And now that this has a proton that can be transferred to go back to a neutral species, it can act as an acid. Which way that equilibrium lies tells us how strong or weak each of these things is. Notice that's what this double arrow here means. It's an equilibrium. Half arrow one way, half arrow the other way. It can go back and forth in that reaction. All right. So by measuring that, we can get a relative scale of where things are as far as they are acidic or not. So the first thing I want to do is I want to look at this side of the chart right here. And I want to show you that we've measured these, and that's why they're in this specific order. But I wanted to show you something very important here. Okay, so we saw that by inductive effect, by ion size, that HI, hydroiodic acid, is more acidic than HCl because it can share that charge more. So we see it above. It's a stronger acid than HCl. And then that's even a stronger acid than the hydronium ion, which is a stronger acid than the carbonic acid here. And then we have, phenol, where is, oh, there it is. Acetic acid is right here. And then we have other things, water and alcohol are way down here. Okay, so if we think about water and alcohol as the weakest acids on this particular scale, there are weaker acids, but these are the ones we're looking at. And as we go up to HI here, they become stronger and stronger. Okay. So that's the acid side of the equation. Okay. If we deprotonate these things and transfer that proton to something else, they become conjugate bases. Okay. So if we had a very strong acid, it becomes a very weak conjugate base. Okay. Think about that. Okay. If I had something that was really, really willing to give up a proton, it's not so willing to accept one. It doesn't have to have one. That makes it a weak base. It will do it, but it's not driven to do it. There's no driving force for it. Okay. So let's look at this hydronium ion right here. So if we take that and deprotonate that hydronium ion, it turns into water. And water is a, relatively moderate base. We looked at on that Lewis acid scale, it was right in the middle. We had halogens, then we had water and alcohols, right? Now, if we moved over one and looked at things with nitrogen on them, that became more basic. And so let's look at that one right there. The ammonium ion turns back into ammonia, which is a pretty decent base. And let's go all the way down at the bottom here. Water turns into hydroxide, and we consider that a strong base. Okay, so the key takeaway from this chart is a strong acid becomes a weak conjugate base. A strong base becomes a weak conjugate acid. Okay, so it's one of those interesting things where if it was strong when it was protonated, it is now a weak base. Now it doesn't have a proton on it. Okay, and things that were very hard to remove the hydrogen on become very good bases. So the less acidic something is, the stronger a base it will become when you remove one of those protons. Okay. So one of the trends you should be able to see there is that when you have an acid that is, your acid can be positively charged, neutral, or negatively charged because you can transfer more than one proton on it. Okay. When a base is negatively charged or neutral, bases can be negatively charged or neutral, but the more negative charge they have on them, the more likely they are to be stronger. And when we look at our acids, we have three different types of acids we have. We have things that just have one proton to transfer, and we call that monoprotic. 2 protons to transfer, that's diprotic. And 3 protons to transfer, that's triprotic. And in our system, we can use many of these, but most organic acids tend to only transfer 1 proton at a time. Okay, so let's look at carbonic acid as one of those organic kind of things. It's kind of like a carboxylic acid without another chain on it here. And so what we have is if we drew the Lewis dot structure of the carbonic acid itself, carbon here, hydrogen, and a hydrogen here, okay? And so it can have 2 protons it can lose. If it loses the first proton here, it's going to generate a negative charge, which luckily can be delocalized over a couple different atoms. But it then can also lose that second one, giving us our di anion here, but it has 2 protons to lose. But each of those protons has a different acidity. The first proton's easier to remove because we have 2 of them available and it can delocalize a single negative charge over 2 atoms. When we remove the second one, it's harder because now we have to balance 2 negative charge over 3 atoms. And so they becomes more charge dense. Okay. And the last thing I want you to remember about that table up there is that some things can appear as both an acid and a conjugate base depending on whether or not they have been protonated or not. So that means those things like water and the ammonia and the quaternary ammonium salt can act as both acids and bases in organic chemistry because of whether or not the thing is more or less acidic than that compound itself. Okay, and the key thing you must take away is the inverse relationship between acid strength and acid and base strength of the conjugate base. Very strong acid, very weak conjugate base. Very weak acid, very strong conjugate base. All right, questions about the other acid types and that general scale of acid, conjugate base, base, conjugate acid. Okay. All right. Well, while you're thinking of that and either typing it in or trying to find the unmute button, I'm going to go ahead and pull up our last goal, which is goal 3. And that's all about pKa's, where we got them and what the relative scales are. Knowing, the relative position of these things is going to help us understand whether the reaction is going to move forward or not move forward. Okay. So, Pka and its conjugates. Okay. So, like I said on the last slide, we have what we call strong acids. Okay. A strong acid, when it almost completely transfers its proton as soon as it can. Okay. So most of the strong acids we see are things like the inorganic acids, the HCl, HBr, HI, nitric acid, sulfuric acid, those kind of things. Now, most of the strong bases are those that react almost completely with water to form hydroxide. And so in those cases, we have, again, the classical inorganic systems of lithium hydroxide, sodium hydroxide, potassium hydroxide. But in organic systems, we rarely have it almost completely transfer a proton in this way. Okay. So that gives us to the idea that most of the things we're going to be looking at are what we would call weak acids. Okay. By weak acid, I don't mean that, oh, they're all weak and so they're not going to react. By weak acid, I mean they don't completely dissociate in water. It doesn't transfer all its hydrogen off. Okay. Now that's important, because if it doesn't transfer all of its hydrogen off, that means there's an equilibrium. There's only some of it is still the molecular acid, but some of it is made into that ion. Okay. So for example, if we took acetic acid and dissolved it in water, about 4 in every 1,000 molecules are converted to acetate ions. That means in your bottle of vinegar, 99% of it is still the acid, because it's a weak acid. It doesn't have to transfer that hydrogen off. Okay. Now, weak bases are similar to that, where they don't completely dissociate in water, so they don't form a lot of hydroxide, but they form some hydroxide in solution. Okay. So weak doesn't mean it doesn't transfer, it just means it doesn't transfer completely. So that means there has to be a scale, because if it doesn't do it completely, there has to be an equilibrium associated with this. Okay. So if it doesn't completely go there, that means that you're going to have some of it as the acid and some of it as the conjugate acid and some of it as your base and some of it as your conjugate base. Okay. So in this case, our acid will be transferred to our acetate ion, and our water is going to be converted into our conjugate acid. Okay. So when we measure the concentration of the hydronium ion times the concentration of the conjugate base divided by the concentration of the acid, we end up with an equilibrium constant about how much it's going to do there. And that value is what we call the Ka. It's just telling us that in this situation, more of it is the acid or less of it is the acid. Okay. Now we typically, once we do that, because these can be very weird big numbers, we actually take the log of it. And so that takes it down to a simple scale. It takes us from about -10 up to about 50. And so it's much easier to comprehend the number. Okay, so if we do that, if we actually dissolved these things into water and we measured that equilibrium constant and then we calculated out that equilibrium and took the log of it, we end up with what we call our pKa value. Okay, so I'm going to use pKa value as a relative idea of how whether things are very acidic or not very acidic at all, and in contrast, how strong the conjugate bases might be if they were weak acids. So this table's a little bit upside down from the previous one. Okay, but what I want you to see here is that if we look down at the bottom here first, HI, we saw that on a previous slide that was a strong acid, right? And by definition, it's a strong acid because it kind of completely dissociates in water. And we see that because when we take the log of something less than 1, it turns into a negative number. So all of our classical strong acids have a pKa of 1 or below, and most of them are below 0. So if you see a pKa in the negatives here, think very strong acid, very easy to deprotonate. Okay. Then as we move up, we get up to our most acidic, organic compounds, and we call those like acetic acid and benzoic acid. And so it's a carboxylic acid on a benzene ring. That's what this one is. And what we see is that we are now in the positive regime, okay? So we have a pKa of about 4, okay? What that means is a pKa of about 4 is that only about 4 of those molecules are dissociated completely. Most of them are their molecular structure. Okay. So now as we go up to something like carbonate ion right here, it's going to lose that last proton to become carbonate here, and that last proton is not very acidic. Okay. So if we look at carbonic acid, we looked at the Lewis dot structure of that. We said that first proton comes off, but it's like a carboxylic acid in the fact that it's not a strong acid. It has a pK of around 6.5. And that generated this right here. But it still had a proton to transfer. But that proton is harder to get off, so its pKa for that second proton is jumped up to around 10, making it a weaker acid. Okay. So let's now look at water. We saw water as that middle of the road guy that it can or lose it, or it can act as a base. And to lose that first hydrogen to generate hydroxide has a pK of about 15.7. Okay. And we said that was about the same for alcohols because that's where it lies on the periodic table. And we see that that's about the same for that. Now, jumping up to that next element, that nitrogen, it makes it more basic, which means it's less acidic. So trying to get that hydrogen off of this nitrogen here is kind of hard. But once we do that, it creates a very strong base. And we'll see that when we do a lot of chemistry. And this last thing we have up here is that nonpolar carbon-hydrogen bond. And it has a pKa of 51, making it really, really bad acid. In fact, you have to hit it with some incredibly strong base to even pull that proton off. And once you create that anion here, this is super, super strong base. It's like one of the strongest bases we get to play with in this class. And we'll see that because it was such a poor acid, you wouldn't even think of it as an acid except if we thought about it in these Lewis acid base theory. Once you do deprotonate it, it becomes a really, really strong base. Okay, so what I want you to we're going to have a few things you want to kind of memorize, like acetic acid's around 4.7, water's around 15, and then we're going to see where the other, alkenes and alkanes and alkynes show up on this list as we move forward in our looking at other functional groups. Okay. So how do we know if something is going to react or not? Okay. So this is where that acid-base concept comes in, the idea that you have an acid and it turns into a conjugate base. And then you had a base and it turned into a conjugate acid. Okay. So the way we decide which way the equilibrium goes is we don't want to compare the base strengths. So we're just going to compare the acid strength to the conjugate acid strength. Okay. And the equilibrium will always fall to the weaker acid or base. Okay, so if we compare just the acid to the conjugate acid, we can see which one's weaker, and we'll know that the equilibrium shifts in that direction. Let's show you how to do that. Okay, so for example, let's start with a pKa. We know acetic acid has a pKa of 4.76. Okay, and so we consider that it's a strong acid for an organic. It's not a strong acid, but it's a strong organic acid. And then we'll react it with ammonia. Notice I'm not using a pKb or anything like that. We don't need that. We only need the acid, the pKa. And when we deprotonate this, it turns into this base. Okay. Now, is it a weak base, strong base? I don't know. We haven't measured that yet. Let's just look at what happens to the ammonia. When we protonate the ammonia, it is now the acid. It's the thing that can transfer the proton. So now, by comparing the strength of the pKa of the acid on one side of the equation to the pKa of the other acid on the other side of the equation, in this case, the conjugate acid of the base, by seeing which one is the weaker acid, we can tell which way the equilibrium lies. The equilibrium always goes from strong to weak, trying to get to the weaker ones. So in this case here, because the acetic acid is stronger than the ammonium ion in the acidity scale, that means the equilibrium is going to be shifted toward this. Does it mean it's completely shifted? No, there's still equilibrium. It's just it's shifted more toward one side. In fact, I'm going to redraw this as it's shifted mostly this way, but a little bit that way. Okay. This is how we use that acid conjugate acid system to figure out whether a reaction is going to move forward or not, and how far we think it might move forward based on this equilibrium. The greater the difference in the acid strengths here, the more it shifts to the weaker side. The less difference, the less it shifts to that side. So we can see the relative amount at which the reaction is going just by comparing the pKa of the acid and the conjugate acid. All right, questions on conjugate acid base pairs? Questions on relative acidity? The idea that we only have to look at the two acid pairs, figure out which one's weaker, and know that the reaction is going to shift in that direction.
Hi, I have a question.
Yes.
When we're giving problems, are we going to be given the pKa value, or our best bet is to memorize some and try and go off of that?
The best bet is probably to memorize about 4, which would be acetic acid, water and alcohol, and then ammonia. Let's see, those are the ones we're going to use a lot. And then when we get to the hydrocarbons, we're going to have those 3 that you just need to get into the correct order. Okay. If they're really close together, I will give you the pKa's, but I want you to know the relative scale is more important. Okay?
Okay, thank you.
Okay, that is my last slide for acids and bases here. Okay. Again, this is to address the real big concepts. There are little concepts associated with this, and that's where the other videos come in. or if you prefer reading the book, this would be a great time to read the book and double check to make sure that the trends are getting in your head. Again, this acid-base thing is all about the Lewis acid-base definition, where the electrons came from to make that new bond, and that looking at the pKa's to decide whether the reaction is going to move to which side of the equation. Okay. All right, well, those are what I have. If you have questions, go ahead and hang out a little bit, and you can ask questions in the Zoom chat or not. Other than that, I will actually stop recording, and I'll have this uploaded in about 30 minutes to an hour. It takes a little time on the YouTube side to process, but I'm going to go ahead and stop recording.